Hi. So today we will be solving another interesting problem. Number 240, search a 2D matrix 2. So the problem says write an efficient algorithm that searches for a target value target in a m cross n integer matrix. The matrix has the following properties. Integer in each row are sorted in ascending from left to right. Integers in each column are sorted in ascending from top to bottom. Okay, so we need to search for a target in a m cross n integer matrix. So definitely one thing is sure that we are going to apply binary search. So one thing or one technique that I can think of, one algorithm that I can think of, is to look for the target element in every array. So what we can do is we can search the target element in every array, and when we find that element we're gonna return true, and if we traverse the whole 2D matrix and we didn't find anything, then we'll return false. And to find element in a and to find an element in a array, the best approach is binary search. So that's gonna be our technique number 2, and then we can look into how we can improve that binary search, that how we can modify that binary search that we have developed initially. So yeah, that would be our two methods for solving this problem. So let's write it out. Okay, so we are going to look at that for every array in matrix, and we are going to design one function called binary search, and we are going to pass our array and target into that binary search, and if that function returns are true, we say that target is in our 2D matrix, otherwise we'll return false. And now we'll write our standard binary search. Array and then target t. So we'll take two pointers, left and right. We'll keep left at 0 and right at length of array -1. Now until left is less than or equals to right, we'll check if our we'll first need to calculate mid. So there are different ways to calculate mid. Mid can be calculated like this: L r plus L divided by 2, or you can also do r plus L divided by floor division, or in Python you can also do r plus L left bit shift by 1, or the standard integer overflow method like r minus L divided by 2. So choose whatever you wanted to choose. Now we'll say that if our mid element is equals to target in a row, in an array or a row, then we'll return true. Otherwise we'll check into where does our mid lie. So if our mid is more than target, then we know it is for sure we need to decrement our right pointer and bring it to mid, otherwise else. So the else case is basically if array of mid is less than target, then we need to increment our left pointer to the mid +1, and we'll return in the end. If we did all the search and we didn't find the element in the array, will return false. So the moving of pointers, I see it like this. So this is our one array which is in increasing order, and these are our initial position of left and right pointers. And first we'll calculate the mid. So our mid is here, and we'll see the value of the mid in the function. So this function could be anything. Today it's array, tomorrow it could be a linked list, it could be a tree, or it could be a graph. So don't need to worry. And where is our target? So if our target is below, if the target lies here, f of t, the target, then we don't need to look for the element in this region. We are sure that our target is going to be definitely over here in this region. So all we need to do is bring our right pointer towards the mid and precisely to be one level below. And in other case scenario, if our mid is over here and the mid is above the target, in that case all we need to do is we need to bring our left pointer to the mid. So in that scenario we'll start looking into this region. So this way we'll keep shortening our search area and until we reach to the target. So that's the standard binary search. So yeah, let's run our problem and see how fast it is. So let's run the test cases. Okay, let's submit our code. Yeah, it's pretty good, it's pretty fast, it's pretty amazing. So that's the one way, and the time complexity for this one is O of m log n, where m is the number of lists, array or rows, and n is the number of elements in each row. Okay, now the interesting question is how much is our now can we improve this? So yes, we can improve this because we are given this condition, like integer in each row are sorted in ascending from left to right, and integer in each column are sorted in ascending from top to bottom. So we can utilize these two properties to make our binary search better, improved version. So what we can do is we can look for the element in the whole I would say in the whole 2D matrix simultaneously. So for that I need one example case. Okay, so let's pick this. So and here is how we can do it. So what we'll do is we'll keep two pointers, one, so I don't want this. So we'll keep one big pointer called R and one small pointer at the start of the each list, and we'll check if where does our element target lies. So if our target element, so let's say this is 5 and this 5, and for the first value that we are checking it's 18, and it is definitely 18 is definitely bigger than 5. So what we need to do is we need to decrement our R pointer to the last one cell above, one row above, and we'll again start column from the beginning, C pointer from the beginning. So again we'll check for the first element in the list, and if it is more than the target, then again we need to decrement our row, and again we'll look. So now in this case we have found one value which is less than the which is less than the 5. So what we'll do is we'll increment our C pointer in hope that we can find the target element in this array. So if we find it, then we'll say return true, otherwise we'll decrement or again decrement our row pointer. So again we can go for, again we'll go into one search below, and again our C will start, but this time our C will definitely start from this position that we have found. So here we'll find our target element and we'll return true in this case. So this is another variation of binary search. We can write it, and we'll have m rows and n number of columns. So the rows are length of matrix and the columns are length of matrix, means basically the length of each 2D, each list in our list of list. So which could be attained by finding the length of the any of the list. And we'll start our search from the bottom left. You can start from top right as well, no worries in it, but I prefer to write it from bottom left, so I'm gonna do that. And our columns will be 0, starting from 0, and we'll write our while loop. Well, while loop has a condition which we need to find out, and because our row is going to be decrementing and columns are going to be incrementing. So the condition would be that row can go up to maximum of 0 and columns can go maximum up to the length of the columns, which is n. So, and now we'll check where is our value in this matrix, and if it is equals to the target, then in this case we'll return true. Otherwise, if the value is more than the target, it means that all the elements in that particular row is more than the target, so we need to go a row above, then above the current row in which we are, to look and search for the target. Otherwise the other case is basically this. So in this scenario, all are, in this case, the which I explained earlier, that all our element values are greater than the target, but not all values. So this is the case over here. So if we have found the value 3 is definitely less than 5, so we need to increment our column pointer by 1, and we'll start again looking into, we'll start the search again into this row. So, and let's run our, and if we do not find anything, then we'll return false at the end. So that would be the improved binary search. Let's run our code and see how it performs. It is returning also true for the test cases, and let's submit our code. So it is also similar. So now the main question, that is, out of both the methods that we discussed, the first one, first binary search and the second binary search. So the first has a time complexity of O of m log n, and the second has a binary, and the second algorithm has a time complexity of O of m plus n. So in this, which is better? So it is actually a trade-off. So basically, in the long run, how we can check this? So let's say our m is 10 raised to 4 and our n is also 10 raised to 4. So then m plus n is 2 into 10 raised to 4, and m log n is 10 raised to 4 into log of 10 to the base 2, which is 4 into 10 raised to 4 log 2 log 10 to the base 2. So clearly we can see that this value is more than 2 into 10 raised to 4. Right, we can also calculate this log 10 if you want. So log 10 can be opened like this: log 10 upon log 2, and I'm opening both of them to the base of 10. So this would become 1 divided by log 2, which is log 2 is 0.3, and which is approximately 3.3, right? So this would become 3.3 into 4 into 10 raised to 4. So we can see that this algorithm in the long run, like for the values of arrays, when they become higher and higher, then the first algorithm that we have written is costlier than the second algorithm. So that's the algorithmic trade-off. And physically, the graph of them, if you want to plot it, so this would be the O of m plus n, the constant time, the linear time graph, and the other one would be, what is the minimum value of n? So we have seen that n is 1. Okay, so m log n log 1 is 0, so this would start from here and it will go until like this. So this would be O of m log n, and yep, so once the m's n are higher, this will continue. So this is that's how you solve this problem, and this is the algorithmic big O analysis of both the algorithms that we have seen today. Okay, so that's how you solve this problem. Hope I'm helping you guys in your journey. Let me know if you want to solve me any particular problem which you are finding difficult, and I can have a look with you guys. Thank you. Please like and subscribe to the channel, and I will continue creating more videos for you guys. Thank you. Have a nice day.